This is the first video on the National 5 Maths topic of circle geometry. In this video we're going to be introducing a few new terms to our circle vocabulary. The first new term is a chord. Okay, so as the text at the right says, a chord is a straight line that joins 2 points on the circumference of a circle. So here in this diagram I've drawn a chord. So it can go from any point on the circumference across to any other point. Diameter, we should know the word diameter. Diameter of a chord diameter is a chord that passes through the center. Okay, so it's this idea that it passes from one side to the other, but goes through the center. A radius, again, that should be a familiar term. A radius is a straight line from the center to any point on the circumference. We've also got this idea of a perpendicular bisector. So, perpendicular lines meet at right angles. If a line is bisected, it is cut into two equal halves. The perpendicular bisector of a chord passes through the center of a circle, i.e. that line is a radius. This diagram here will hopefully make that a wee bit clearer. I've got my radius, which I've drawn in blue, and my chord, which I've drawn in red. I know if I have a right angle where these two things cross over, the chord has been split into two equal pieces. The reverse is also true. If I know the chord here has been split into two equal pieces, I know I've got a right angle there. What I'd like you to do here is take this circle and draw two radiuses on it. I've got this idea that two radii and a chord will form an isosceles triangle. If I show you my diagram, I've drawn in one radius here, I've drawn in another radius here, and I've joined them up with a chord, joined their ends up with a chord. If I think about it, we should see this as an isosceles triangle because my two radii are equal, which has to form an isosceles triangle. It's also worth noting that in an isosceles triangle, those angles would be equal. Okay, so a majority of our problems will be based around spotting these. So either spotting our perpendicular bisectors, this sort of situation, or on spotting isosceles triangles. When we've got a perpendicular bisector, it's possible to form a right angle triangle by adding another radius to our diagram. So on my diagram here, I've added a radius here, and you can see it's formed a right angled triangle. Forming right angled triangles allows us to apply Pythagoras in a selection of problems. We'll also see later in the topic that we can apply trigonometry. Okay, so I'm going to do two examples here. I'm going to find the lengths of OC and CD given the radius 15 and the length of my chord AB is 22. So looking at this diagram, I want to find the lengths of OC, so I will do that first. Now, two pieces of information I've been given is I've been given the length of the chord and I've been given the length of the radius. I've got my right angle here, so it is a case of trying to form a right angled triangle. If I look there, that line I've just drawn in is a radius. I'm able to form a right angled triangle like so. So this triangle is from O to C, C up to A, and the radius would complete it. So I know my radius here is 15 centimeters. I know the red line going down here, A to B, well, that's been cut in half. If I half my 22, that would give me 11. So the line OC here, well, it's the shorter side of a right angled triangle. So I know using Pythagoras, I can square my two sides and subtract them. Once I've done that, second step of Pythagoras, I would take the square root. So this tells me OC is 10.20 centimeters long. Notice how I've written down my unrounded answer and then written down my rounded answer. Good habit to get into at National 5. If I wanted now to find CD, which is this small part here, well, notice how it's part of the whole of that radius. My line CD is the whole of the radius, which is 15, take away that bit there, which is what I've just figured out. It's going to be 15, take away the 10.20, which would give me 4.80. So this question was set up deliberately as a two-part. I had to find OC, I had to find this length here, and then subtract it from the radius to find that length there. Another example here, find the lengths of OH, which is this line here, and I've been asked to find the length of the line CD, this line here. Again, this question will be structured so that the first part helps me find the second part. I formed a right angled triangle. Now, where this has come from, I have been asked to find the line OH. I know DH is 4 because this line here has been split in two. If you notice the two little dashes there and there. That's a perpendicular bisector, so I know I've got a right angle. The 7, well, that's been formed by joining O, the centre, to D. That's my radius. So it's important to remember a radius can be drawn anywhere on my diagram. Pythagoras, I know my hypotenuse, I know one of my short sides, so I'm going to do 7 squared minus 4 squared, gives me 33. Square root of 33, 5.7445. So OH is 5.74 meters, rounded to 2 decimal places. A new diagram for the second part. To find CD, this line here, well, I'm using DH as before, this line here. I know the radius, and I figured out OH, so I can add it on there. This is what I've done here. I've taken my radius of 7 and added my 7.4 to give me that. I'm looking for the hypotenuse here, so square them and add them. Take the square root of that and round that to 2 decimal places. So I can see that line CD is 13.36 meters. The bottom half of this page shows what's a very typical exam question. I've got a water pipe shown is 48 centimeters in diameter, and the surface of the water is 29 centimeters wide. So looking at the diagram, 48 all the way across, the water level there, 29 across. And I've been asked to find the depth of the water. So I'm really looking for that distance there. I've got a circular water pipe. So the key to this question is going, the center is here, and drawing 2 radii. If I draw a radius straight down through the center, I formed a perpendicular bisector. So I've got a right-angled triangle. I know that this line here has been split into 2 equal halves. My second radius, actually I can draw in like that, well, that forms a right-angled triangle. So I've got my 24 centimeters for this line here, which is half the diameter. I've got 14.5 centimeters for this line here, which is half of this water level. I can use Pythagoras, square my numbers and subtract them. So I would square 12 and subtract 14.5 squared. Typing that in as a oneer. Then I would take the square root. Now, you'll notice how I haven't rounded at this stage. That's because I'm not finished the calculation. I need to use this 19.1245. And I just want to make sure I'm being accurate, so I'm going to use the answer button on my calculator. To find the depth of this part here, well, I know the whole of this line, up and down the way. If I take away this top part, I'll be left with the water depth. So I've taken my radius and I'm subtracting my previous answer. So I'm going to do 24, take away my previous answer. So I'm using the answer button. Again, written down my unrounded answer, and then I've rounded to 1 decimal place at the end here. The point in this is, if you round in the middle of a calculation, you can potentially make little rounding errors that would add up later. This question's a challenge question. You can have a go at that. We will look at this in class next lesson though. 3 hints. If you don't want to know what the hints are, you can stop the video and try and attempt the question. If you want the hints, here they go. The first hint would be, find an expression for the length of OR in terms of x. Now notice x is my radius. Notice how I've been given these 2 pieces of information too. The next thing you would do is I want you to use Pythagoras to form an equation in terms of x. Final step would be to solve that equation to find x, the radius of the circle. Give that a go.